This research paper introduces the MELODI framework, a novel tool designed to monitor and analyze energy usage during the inference phase of large language models, LLMs. The urgent need for such a framework stems from the growing environmental and economic costs associated with the operation of LLMs. MELODI leverages two specialized power usage monitoring tools, Scafandry and NVIDIA, to track the CPU and GPU power consumption for the LLM process. This framework facilitates the collection of metadata associated with LLM inference tasks, enabling a deeper analysis of the relationship between task complexity and energy utilization. The paper also presents a robust dataset essential for evaluating MELODI's capabilities. This dataset includes a diverse set of prompts to monitor the energy consumption of various LLMs across different types of instructions. The data collection includes not only energy consumption measurements but also related metadata, such as the size and complexity of prompts, the responses, and the time metrics for each inference process. This rich dataset helps explore the relationships between prompt complexity and the energy expenditure they incur. The research provides three main contributions. Firstly, it has developed a framework integrating open-source tools to monitor power and energy consumption during the inference phase of LLMs. Secondly, it has undertaken an extensive data collection initiative involving a variety of language model deployment frameworks, multiple LLMs, and diverse prompt datasets to facilitate a comprehensive comparison of energy consumption across these dimensions. Thirdly, it offers a generalized analysis that elucidates the relationships between prompt characteristics, such as length and features, and the energy consumption patterns observed within the collected data. In addition, the paper discusses the background of LLMs, which represent a significant advancement in natural language processing and deep learning. These models, trained on vast text datasets, learn intricate language patterns and relationships through unsupervised learning, predicting subsequent text from context. The integration of LLMs into digital ecosystems is underpinned by advanced APIs and deployment frameworks. These APIs are essential tools that allow developers to use LLM features for prompt submission and response generation, making it possible to add LLM capabilities to various applications. Finally, the paper highlights the importance of advanced monitoring tools and technologies for tracking and optimizing energy consumption, thereby mitigating the environmental impact of AI operations. MELODI employs Scafandry and NVIDIA for their complementary features, providing detailed insights into the energy usage of computing systems at the process level and real-time monitoring of GPU, including power consumption, for systems equipped with NVIDIA GPUs. The MELODI framework is a tool designed to monitor the energy usage of large language models, LLMs, during their inference processes. It systematically samples prompts from a curated collection, submits these prompts to an LLM, and records the prompts, responses, metadata, and energy metrics during inference. The framework integrates two power monitoring tools, Scafandry and NVIDIA to track the power consumption of the deployed LLM, providing a comprehensive view of energy utilization. The dataset used in this study includes alpaca and code feedback datasets, featuring a diverse range of prompts tailored to enhance instruction following capabilities and refine code execution. The LLMs involved in the data collection process range from CodeLlamma 7B to Llama 370B, with varying average energy consumption and response token lengths. The hardware setups used for data collection encompass high-end servers, workstations, and laptops, capturing data from different operational conditions. The energy consumption dataset obtained using MELODI includes an array of data points per sample, such as prompts, responses, token lengths, timestamps, time series data on power usage, and aggregated energy consumption of the LLM service during inference. This dataset is analyzed to address three research questions: how the energy consumption of LLM inference varies across different hardware, models, and prompt datasets, how the energy consumption of LLMs changes as a function of the number of tokens in the input prompt, and whether the energy consumption of LLMs can be predicted using the input prompt's characteristics. The study explores the energy consumption of large language models, LLMs, during inference processes, focusing on model size, hardware configurations, and prompt datasets. The analysis is conducted using statistical methods, visualization techniques, and predictive modeling. In terms of model size, larger models such as Llama 70B and Llama 370B exhibit significantly higher energy consumption per token compared to smaller models. This difference in energy use is substantial, with larger models consuming roughly 100 times more energy per token than their smaller counterparts. Hardware configurations also play a crucial role in energy consumption. LLMs running on laptops show higher energy demands compared to those on workstations, primarily due to inefficiencies in CPU processing. However, when comparing models of the same size, differences in energy efficiency are observed. For instance, Llama 7B consistently displays lower energy consumption than Gemma 7B. Prompt datasets also influence energy consumption. The code feedback dataset leads to higher energy use per token compared to the alpaca dataset, likely due to longer response lengths associated with the former. This observation is supported by Table 4, which reveals that the median energy consumption for the code feedback prompt dataset exceeds that of the alpaca dataset during inference. To investigate the relationship between prompt complexity, response characteristics, and energy consumption, the study employs various Python frameworks to derive 57 text-based features. These features are then integrated with the energy consumption dataset, and the Pearson correlation coefficient is calculated between energy consumption per prompt and each feature. Table 5 presents the top 20 features from this analysis, providing insights into the relationship between text complexity and energy consumption. The findings underscore the importance of considering both model size and hardware configurations when optimizing the energy efficiency of LLMs. Moreover, the choice of prompt dataset can significantly impact energy consumption, highlighting the need for careful selection of datasets in energy-conscious applications. The predictive models developed in this study could be instrumental in accurately forecasting the energy consumption of LLMs based on prompt features and response characteristics, ultimately aiding in the development of more sustainable AI systems. This research examines the correlation between input prompt features and energy consumption per response in large language models, LLMs. The analysis reveals that response characteristics, such as token length and duration, are strongly correlated with energy consumption, whereas prompt complexity features exhibit low correlations. The results suggest that optimizing the response generation process could be more effective in reducing energy consumption than simplifying input prompts. To address the research question of predicting energy consumption, the authors developed machine learning models using the energy consumption dataset, focusing on either prompt or response characteristics as input features. Random forest, RF, models were identified as the optimal choice, and their performance was evaluated across various hardware setups, models, and prompt datasets. The RF models using response token length demonstrated high predictive performance, with most achieving an R2 score greater than 0.97. However, models for CPU-only laptops performed poorly, indicating potential inaccuracies in CPU-based energy estimates. In contrast, RF models relying solely on prompt characteristics exhibited limited performance, with variable R2 scores across different models. The findings highlight the importance of constraining response lengths to reduce energy consumption during model operations. The study also identifies limitations, including the accuracy of power usage monitoring tools and the small dataset size, which constrains the generalizability of the results. Future research directions include utilizing more precise power measurement tools, exploring the potential of using LLMs to analyze prompts for energy consumption prediction, and investigating the connection between prompt complexity and energy consumption. The study's results emphasize the need to consider energy consumption in LLM operations and provide insights into optimizing response generation to reduce energy usage. The analysis presented on pages 9 and 10 delves into the energy consumption of large language models, LLMs, during inference. It discusses the need for energy-efficient practices and the importance of understanding the relationship between response quality and energy consumption. The authors highlight the limitations of current studies and propose a comprehensive framework, MELODI, for real-time energy tracking and optimization. MELODI leverages scafandry and NVIDIA to measure power usage, enabling a more dynamic energy efficiency optimization. The framework's capabilities are demonstrated through data collection on various LLM architectures, hardware setups, and prompt datasets. This approach facilitates a deeper understanding of energy dynamics associated with LLM deployment scenarios, contributing to the optimization and sustainability of LLM applications. The authors also acknowledge the funding support from the European Commission and reference several studies on sustainable AI and energy-efficient computing. The summary begins with the discussion on the energy costs of large language model inference, highlighting the work of Siddharth Samsi et al. On benchmarking the energy costs. It then transitions to the topic of environmental risks and benefits of large language models, referencing Matthias C. Rillig et al.'s work on the subject. The discussion continues with the focus on the energy and policy considerations for deep learning in NLP, as presented by Emma Struble et al. The section also touches on the taxonomy of risks posed by language models, as detailed in Laura Weidinger et al.'s work. The summary concludes by mentioning the part-time power measurements and the OpenCode interpreter, showcasing the diverse range of topics covered in the research.